Welcome back. As promised, now we want to jump into the appendix and look at this example of ER visits. So, for ER visits, we want to think about a practical example of where we might use probability distributions. Let's say that I'm a hospital administrator and I'm trying to to estimate how many emergency room visits there might be to my hospital tomorrow. Maybe I need to schedule the staff. I'm wondering how many people do I need on call tomorrow? How many do I need coming in? Nurses and doctors. And so I want to have some guess of what is going to happen. But I can't know for sure. It's not like I can perfectly predict the future. Instead, I just want to know what are some of the possibilities and how likely are different possibilities. Suppose that I have access to daily data from the past year, which tells me how many ER visits there were every day last year. So that gives me maybe a starting point to try to project forward and think about what the possibilities might be tomorrow and how many staff I should schedule for tomorrow. The question is, how might I go about creating an estimate of how many ER visits there will be tomorrow? So you could think about this a little bit on your own. And there are multiple ways we might think about using that past data to create some estimates. But I'm going to jump into some examples of some ways that I might try to think about this. So, as I sort of acknowledged or alluded to earlier, I can't perfectly predict the future. And part of the reason for that is that there's going to be lots of factors feeding into how many people visit the ER tomorrow that I can't perfectly predict. I don't know necessarily what tomorrow's air quality is going to be, and that could affect if people have respiratory problems, for example. Maybe I can have some sort of forecast for air quality, but I can't know exactly what it's going to be. I don't know what people's physical activities are going to be, what kind of accidents might occur, right? I just can't perfectly predict the future. So instead of perfectly predicting the future, I want to think about what are some possibilities. And that's going to be linked to this idea of probability distributions, right? Because, like I said, they're motivated by the fact that there's uncertainty and we want to think probabilistically about what could occur. So, to make this example work, I've actually pulled some real world data from a project that was published. There's a paper that was published, and they published the data that they used for their paper. And just to be clear, this data comes from 2011, so it's a little bit old, and it's not coming from a single hospital. It's actually reporting on 30 different hospitals in the city of Seoul, South Korea. So we're going to look at real world data because it's going to make a useful example, but just letting you know where that real world data came from. Here's some example of what this data looks like. So this column is showing the number of ER visits, but specifically for circulatory type problems. I'm not a doctor. I don't know a lot of details about how to categorize different types of ER visits. But the main thing that I'm pointing out is just this is not all ER visits. This is a certain type of ER visit, but this is how many are occurring each day across these three hospitals. So on January 1st, there were 134 visits to the ER for this type of problem. On the 2nd, there were 126 visits, and so on and so forth. This is what the data looks like. I've just shown the first 4 days, but like I said, it's for the entire year. So here is a histogram for the entire year of how frequently different values occurred. So what do we call this? All of the different values and how often they occurred? It's called a distribution, right? That's the term that we learned at the beginning of this lecture. So this is a distribution. We want to think about creating a probability distribution. Again, a distribution is data that we've already collected, what we have plotted here. A probability distribution is talking about possibilities for the future, right? What could occur and how likely are different values to occur. So we can think about constructing a possible probability distribution. It might not perfectly predict the future, but at least it could give us a decent guess based on this data that we have from the past, assuming that the past is going to be a good way to predict the future. So, if we want to make a prediction for the future, one thing we could do is just say, well, the average or median value is around 130. So that's my guess for what tomorrow will be. Maybe we'll have 130 people visit the ER tomorrow. But that's not a very sophisticated guess because it's just a single, we call it a point estimate a lot of times. It's a single number. Maybe we'll want to think about a range, right? It's not that every day 130 people come in, right? There are good days where we have fewer than that, and there are bad days when we have more. So how can we think about describing possibilities for tomorrow in a more sophisticated way beyond just my best guess is it might be 130? So the way that we can do that is as I alluded to already, with a probability distribution. We're going to say there's different possible values for how many people could come in tomorrow, and they're not all equally likely, right? It's probably much more likely that around 130 people come in than that 90 people come in. 90 people seems like a possibility, but a rather rare one compared to 130 or 140, right? So a probability distribution is going to give us kind of a formal way to make more precise predictions. Perhaps the simplest probability distribution we could create as an estimate for tomorrow's visit would be to just use the exact percentage of times that each value was observed in the past year. So I've redrawn this histogram, but now I've made it so that each bin only corresponds to a single number, a single value, right? Before we had a whole range of values that were being represented by each bar, right? Maybe this ranges from 98 to 104 or something like that, right? So we can see how tall this is, how frequently a number in the range of 98 to 104 occurred. But in this new histogram that I've drawn, it's just showing single values. So it's more precise, right? So we can see how many times the value, I think this is probably 99 occurred. It looks like the value 100 never occurred, but maybe 102 occurred a couple times or something like that, right? If we want to be more precise, we can actually in Stata, you can run the tab command and get exact values, and then we can see exactly how often each of these different values occurred. So you can see that there was one day when 84 patients came in for cardiovascular admissions, and there were no days when 85 patients came in. There was one day when 86 patients came in, and then it looks like we have another gap. No days did 87 patients come in, 88 patients come in, 89 patients come in. We didn't see those values at all, but we did see a 93. One day, 93 people came in. There are 5 days when 114 people came in, 12 days when 115 people came in, right? So this is the same data as being depicted in this histogram, but it's a little bit more detail, right? It's hard to tell because of how many observations are here, how many values are here, exactly what number each of these bars corresponds to. So this view tells us much more precisely, right, than we can read from this graph, but it's the same data. So the question is, do we want to create a probability distribution projecting into the future where we just say, okay, an 84 patients coming in happened 0.27% of the time. So therefore, I think that there's a 0.27% chance tomorrow that we get 84 patients. I think that tomorrow there's a 0.27% chance that we get 86 patients. That's one way we could create our probability distribution. And this could be represented visually like this, right? We're saying that there's that big of a chance that we get that many observations tomorrow, so on and so forth. But what's the potential problem with this? Well, one problem is that there are a lot of values that never occurred, right? We never had a 90, for example. We had a 93 and we had an 86, but we never had exactly 90 patients come in. Well, just because we never had that occur in the year that we're using to project forward, it doesn't mean that there's a 0% chance that we have 90 patients tomorrow, right? And in particular, 90 is a plausible value. It's maybe not a super likely value, but because we had an 86 and we had a 93, then we would think that a 90 should be plausible. In the same way, we can see that we had a lot more times when 115 or 117 occurred than we did 116, right? You can see that if we just take the past and say this, however many times this occurred in the past is how likely it is to occur in the future, we're going to be implicitly arguing that 115 or 117 are much more likely to occur than 116 or 114. And to be more specific, it's about twice as likely that we would get a 115 or a 117 as it is that we would get a 116 or a 114. But does that really make sense? That it would be twice as likely that we get one of these values as its neighboring values? I would say no. It's probably just dumb luck that one of these values occur twice as frequently. And in general, when we have a finite sample of data, one of the things that we worry about is that it's going to be a little bit noisy. And in particular, we probably want to smooth this out is one way we can describe it, right? There's some choppiness in the data, right? Tall bars right next to short bars, but it probably isn't anything systematic, right? There's no reason to believe that 117 patients are much more likely to come in tomorrow than 116, right? These two probabilities should be similar if we're trying to project to the future. So maybe we need to smooth a little bit to get rid of some of this choppiness in the data. So this is in words going over a lot of what I already talked about. except now we're adding a potential solution. Use one of the well-known distributions that statisticians have come up with to model different types of data generation processes. And we haven't talked yet about the fact that statisticians have come up with these different probability distributions, but we'll return to that when we go back to the main slide. So we're foreshadowing this a little bit with an example. We're going to try a particular distribution that we'll learn more about in the main lecture slides called the normal distribution. And you can see this is what it looks like. This solid line is the normal distribution, or one version of the normal distribution. And if we plot that over our data, you can see how we have now a nice, smooth distribution, probability distribution that we can use as the basis of our predictions. In other words, rather than having this choppy model where it jumps up and down, based on what happened in the past, the choppiness that we saw in this figure, you can see that the normal distribution gives us this nice, smooth distribution, which is probably more realistic, right? We probably don't buy that that choppiness is going to continue on into the future in that exact same pattern. It makes more sense to smooth things before we make a prediction about the future. So we can make our analysis even more sophisticated if we take into account some additional factors. But this, what we already did right now, this is a good way to think about predicting the future, right? We take patterns from the past, but then we try to smooth those a little bit, and it gives us a probability distribution that of how likely different values are to occur in the future. That's what we mean by a probability distribution. Okay, if we do want to get a little bit more sophisticated, though, we could think about taking into account, I don't know, weather conditions or different days of the week, something like that. So let's try doing just one additional factor, which is different days of the week. And you can see I've now, instead of showing histograms, I'm showing box plots. And we can see how many ER admissions happened in that year for different days of the week. So do we see any patterns here? Does it seem like there's differences in terms of how many ER admissions there are depending on the day of the week? Well, yes, in fact, there are, right? It looks like Monday, the mean is noticeably higher, or sorry, the median is a lot higher on Monday than it is on Sunday. In particular, we see that on Monday, the median looks like it's about 132, 133, something in that neighborhood, whereas it's down closer to 122, 123 on a Sunday, right? So the median is maybe 10 points higher on Monday than it is on Sunday. So it looks like maybe people on the weekend are putting off going to the ER, or maybe they're not engaged in as much physical activity that sometimes results in having to go to the ER or something like that. But there are patterns throughout the week, right? It looks like Monday and Friday are the peaks, right? You have the most people going to the ER on a Monday or a Friday, and you have fewer going on a Wednesday, a Sunday, or a Saturday, right? With Tuesday and Thursday falling somewhere in between. So this graph kind of shows us it looks like there is a meaningful pattern, that the day of the week is related to how many admissions you have to the ER. It's not a super strong relationship. It's not like nobody goes to the ER on Sundays and they only go on Mondays, right? But it does look like a few more people go on Mondays than on Sundays to the ER. So there is some pattern with day of the week. So in light of that, we might want to change our prediction for how many people we think are going to go to the ER tomorrow, depending on what day of the week tomorrow is and how that pattern looks different depending on the day of the week. So we can think about, instead of having a histogram for every day in the past year, we can make a histogram just for Thursdays. Here's what we get if we make a histogram just using the Thursdays from that year of data. One of the things that we do is now we're only looking at 1/7 of the data, right? We cut out 6 days of the week and we only kept one day, just the Thursdays. And so you can see that now the data looks even choppier, right? Because we have a smaller sample size. And when you have small sample sizes, a lot of times your data is going to look a little bit funnier. But this is how frequently different levels of ER admissions occurred on Thursdays from that year. So we can think about then plotting a normal distribution over this data, making it so that the mean and the standard deviation line up with our distribution. But now we're predicting what we think the different probabilities are after doing some smoothing, right? We see this normal distribution is nice and smooth. Now, it probably should continue out here. I don't know why Stata doesn't continue the plot of the normal distribution over to the side. But just note in your head that this line should continue down to the edge of the graph. Um, Now, if we repeat this for all the other days of the week, you can see that we have slightly different predictions for Sunday versus Monday, right? Here's all the possibilities and how likely we think they are to occur for Sunday. Here's all the possibilities and how likely we think they are to occur for Monday. So you can see that the peak of this distribution is a little bit further to the right, closer to 135 than Sunday, which is down closer to 120. So you can see Tuesday somewhere in between, right? These are our different predictions for different days of the week. Finally, I'll just note that we'll learn more about normal distributions in a moment, but normal distributions are a symmetrical distribution. Not all data from the real world, though, is going to follow a normal or a symmetrical distribution. And you can see that this is a different type of admissions. This is for respiratory admissions as opposed to cardiovascular. And these admissions from that real world data look skewed, right? There's a lot of high end outliers. Maybe that's because respiratory conditions are more related to air quality, if there's pollen or different pollutions in the air, and maybe there are a few days a year where the air quality is really bad and it tends to spike admissions. I don't know if that's what causes these outliers or not. I don't know enough about public health, but there's something. There must be something in the atmosphere that's causing there to be some really a few days that have really large values of respiratory admissions. So whereas the cardiovascular admissions looks much more like a normal distribution, right? It has this symmetrical shape for cardiovascular admissions. For respiratory admissions, we see a different shape. So in the real world, different kinds of distributions will occur depending on what kind of data we're looking at and what the causes of those values are. So there must be something different about what's causing these kinds of ER admissions that is resulting in a different shape of the distribution. All right, that's it for this example with ER visits. Hopefully, it was helpful in especially distinguishing between a distribution of data that we've already collected, what happened in the past, and a probability distribution, which is our guess about what might happen in the future. And that's one of the really key distinctions I want you to take away from this lecture.